In 2018, part of Indonesia's Anak Krakatau collapsed into the sea, which triggered a tsunami and killed hundreds of lives without a major eruption. Volcanic mountains do not behave like normal peaks. They are built from unstable layers of ash, lava, and fractured rock. Entire sections can fail suddenly under their own weight. This documentary examines 8 volcanic mountains with documented histories of collapse and the real dangers they continue to pose. Stromboli has been erupting for over 2,000 years without stopping. Located in the Tyrrhenian Sea north of Sicily, this 926-meter stratovolcano erupts every 15 to 20 minutes with mechanical regularity. Incandescent rock explodes from its summit. Glowing material arcs through the darkness. The pattern repeats endlessly. Ancient sailors called it the lighthouse of the Mediterranean. But Stromboli's greatest danger is not its eruptions. It is the mountain itself. The volcano rises 926 meters above sea level, but extends over 2,000 meters from the seafloor. Most of its mass remains underwater. On the northwestern flank sits the Sierra del Fuoco, a massive horseshoe-shaped scar carved by prehistoric collapse. This is where the mountain failed catastrophically thousands of years ago. The scar remains the primary instability zone. Slope angles exceed 35 to 40 degrees. Hydrothermal systems beneath the surface chemically weaken the volcanic rock. Magmatic pressure builds continuously. The mountain is structurally compromised. In December 2002, 2 flank collapses sent approximately 20 million cubic meters of material into the sea. Tsunamis generated by the debris reached the coasts of Sicily and Calabria. In July 2019, a paroxysmal eruption triggered another collapse. Landslides entered the water. Tsunami waves followed. Both events occurred suddenly. Italy's National Institute of Geophysics and Volcanology monitors Stromboli continuously through seismic networks, thermal cameras, and GPS stations tracking ground deformation. Yet predicting the exact timing of collapse remains impossible. Approximately 500 people live permanently on Stromboli. Families occupy villages built on slopes that scientists classify as unstable. Tourism infrastructure brings thousands of visitors annually to witness the eruptions. The island's economy depends on the volcano that threatens it. Residents understand the risk. They choose to stay. Community and tradition outweigh safety guarantees that do not exist. Stromboli represents a fundamental truth about volcanic mountains. Instability is not theoretical. It is measured, monitored, and inevitable. The mountain has collapsed before. It will collapse again. The Mediterranean's lighthouse burns on, beautiful and dangerous in equal measure. In 1883, Krakatau exploded in one of history's most violent volcanic eruptions. The blast killed over 36,000 people. Tsunamis crossed the Indian Ocean. The sound was heard 4,800 kilometers away. The mountain collapsed into a submerged caldera. 44 years later, in 1927, the sea began to boil. Submarine eruptions broke the surface. A new volcano was born from the ruins of the old. Anak Krakatau, child of Krakatau. The young volcano grew rapidly. Persistent eruptions built a cone that rose higher each year. By 2018, Anak Krakatau stood 338 meters above the Sunda Strait between Java and Sumatra. Then, on the evening of December 22, 2018, the southwestern flank collapsed. Approximately 150 to 170 million cubic meters of volcanic material slid into the sea during what appeared to be routine eruptive activity. No earthquake preceded the collapse. No obvious warning occurred. The debris entered the water and displaced it violently. Tsunami waves formed instantly. Within minutes, waves up to 5 meters high struck coastal communities along both sides of the Sunda Strait. It was a Saturday evening. Beaches were crowded. Hotels were full. The waves hit without warning. 437 people died. Thousands were injured. Entire sections of coastline were devastated. Rescue teams arrived to find destruction that no one had anticipated. Volcanic collapse had generated a tsunami with no seismic alert, no time for evacuation. The collapse removed 2/3 of the volcano's height. Anak Krakatau was reduced to approximately 110 meters. Its entire profile was reshaped in minutes. Indonesia's Center for Volcanology and Geological Hazard Mitigation monitors the volcano, but access remains extremely limited. The island is dangerous. Equipment deployment is difficult. Ongoing eruptions prevent close observation. Since 2018, Anak Krakatau has continued rebuilding itself through frequent eruptions. By 2024, the volcano had grown back to approximately 157 meters. The cycle continues. The 2018 collapse proved a critical reality. Volcanic instability does not require major eruptions to become deadly. Routine activity can mask catastrophic structural failure. Modern monitoring systems exist, but they cannot predict collapse with certainty, especially when no earthquake triggers the event. Anak Krakatau remains highly unstable. It grows higher each year, adding weight to slopes that are fundamentally weak. The child of catastrophe has inherited its parents' violence. And the Sunda Strait watches, waiting. Cumbre Vieja is a volcanic ridge extending along the southern half of La Palma in Spain's Canary Islands. For decades, it sat relatively quiet. Then, on September 19, 2021, fissures opened at the Tajagate vent. What followed was the most significant eruption on La Palma since 1971. The eruption continued for 85 days without stopping. Lava flows advanced relentlessly through residential areas, burying entire neighborhoods under molten rock. Over 3,000 structures were destroyed. Approximately 7,000 people evacuated as lava consumed homes, farms, and infrastructure. The flows covered 1,219 hectares and added new land to La Palma's western coast. But as residents watched their homes disappear, scientists worldwide debated a darker question. Could this eruption trigger catastrophic flank collapse? In 2001, a controversial scientific paper by geologist Stephen Ward and volcanologist Simon Day proposed a scenario that captured international attention. They suggested Cumbre Vieja's western flank could collapse catastrophically, sending a massive volume of rock into the Atlantic Ocean. The resulting megatsunami, according to their model, could generate waves affecting coastlines from Africa to the Americas. The paper sparked intense scientific debate. Most volcanologists strongly dispute the megatsunami hypothesis. Evidence does not support imminent catastrophic failure, but structural weakness does exist. During the 1949 eruption, a 2.5-kilometer-long fracture system opened along the western flank. These fractures remain visible today, evidence of stress and deformation within the volcanic edifice. Cumbre Vieja sits above steep submarine slopes. Any collapse would enter deep water, potentially amplifying tsunami generation. Spain's National Geographic Institute maintains extensive monitoring across La Palma. GPS stations track ground deformation. Seismometers record every tremor. Satellites measure surface changes. Scientific consensus acknowledges that large-scale flank collapse is possible over geological timescales, thousands or tens of thousands of years. But imminent failure is not supported by current evidence. The 2021 eruption did not trigger collapse. Monitoring detected no signs of large-scale flank destabilization. Yet the eruption proved Cumbre Vieja remains volcanically vigorous and structurally evolving. La Palma's 85,000 residents live with this uncertainty. The island's economy depends on tourism and agriculture, both industries directly threatened by volcanic activity. Cumbre Vieja represents the challenge of assessing long-term volcanic hazards. The western flank may remain stable for millennia, or stress could accumulate faster than models predict. Monitoring continues. The debate continues. And Cumbre Vieja, now quiet again after 2021, continues its slow geological evolution. The Atlantic watches. Mount Meager has not erupted in approximately 2,400 years, but the volcano is far from dormant. Located in British Columbia's Coast Mountains, the Mount Meager Massif reaches 2,680 meters at Plinth Peak. Beneath the surface, geothermal systems remain active. Hot springs discharge from the slopes. Heat flow continues. The mountain is alive, but its threat comes not from eruption. It comes from internal decay. On August 6, 2010, the southwestern flank of Mount Meager suddenly collapsed. Approximately 48.5 million cubic meters of rock, one of Canada's largest recorded landslides, detached and plunged down Meager Creek Valley. The debris avalanche traveled 12.7 kilometers at speeds exceeding 100 kilometers per hour. Rock, ice, and pulverized volcanic material roared through the narrow valley, temporarily damming Meager Creek. The natural dam raised immediate concerns. If it breached catastrophically, downstream flooding could threaten communities along the Kīlauea River drainage. Emergency response teams monitored the blockage for weeks as water levels rose behind the debris. The dam eventually eroded gradually rather than failing suddenly. Catastrophic flooding was avoided, but the collapse revealed the fundamental instability of Mount Meager. The cause was not seismic activity or fresh magma. It was hydrothermal alteration. For millennia, superheated groundwater has circulated through the volcanic rock, chemically transforming solid stone into weakened, clay-rich material. The process is invisible from the surface, but internally, the mountain has been decaying. Hydrothermal alteration creates zones of profound weakness within volcanic edifices. The rock loses structural integrity. Gravity does the rest. Mount Meager's instability is accelerating due to glacial retreat. Ice that once buttressed steep slopes is disappearing. Climate change removes the structural support that has held unstable rock in place for thousands of years. Natural Resources Canada has studied Mount Meager for geothermal energy potential. The same heat that weakens the mountain could generate over 100 megawatts of electricity. But harnessing that energy requires infrastructure in a profoundly unstable environment. The Geological Survey of Canada monitors the massif through periodic surveys, but remote location and harsh weather complicate continuous observation. Access is difficult. Equipment deployment is challenging. The 2010 collapse occurred without warning. Had timing differed by hours, it could have encountered workers or tourists traveling to Meager Creek hot springs along nearby access routes. Mount Meager represents a unique category of volcanic hazard, mountains that threaten not through eruption, but through slow structural failure driven by internal processes. No lava, no ash, just rock weakening silently beneath the surface. And gravity, waiting. Pico do Fogo rises 2,829 meters above the Atlantic Ocean, the highest peak in Cape Verde. The name translates simply, Fire Peak. But Pico do Fogo's greatest distinction is not its height. It is where the mountain sits. The volcano rises within Chá das Caldeiras, a massive collapse caldera 9 kilometers wide, formed approximately 73,000 years ago when the mountain's flank catastrophically failed. The caldera walls tower around the volcanic cone, a permanent reminder of past collapse. And inside this ancient collapse structure, people chose to live. Before 2014, approximately 1,200 residents occupied the villages of Portela and Banguera within the caldera. They cultivated crops in volcanic soil. They produced wine from vineyards planted on lava fields. They built homes on terrain created by the mountain's violent history. Then, on November 23, 2014, fissures opened on Pico do Fogo's flanks. Lava erupted directly toward the villages. Within hours, flows were advancing through agricultural fields. Within days, they reached the first structures. The eruption continued for 77 days, from November 23, 2014 to February 8, 2015. All 1,200 residents evacuated. No lives were lost. But both villages were destroyed. Lava buried homes, schools, and community centers. Agricultural land disappeared beneath flows. Wine production infrastructure, critical to the local economy, was consumed. Approximately 4.8 square kilometers were covered with new lava. The 2014 to 2015 eruption followed a familiar pattern. In April and May 1995, Pico do Fogo erupted similarly, damaging settlements and forcing evacuations. The cycle repeated: eruption, destruction, evacuation. And yet, after both eruptions, residents returned. They began rebuilding inside the caldera. New homes rose on slightly different ground. Vineyards were replanted in fresh volcanic soil. The fertile soil draws them back. Generational ties to the land run deep. For many families, leaving Chá das Caldeiras means abandoning identity. Cape Verde has limited resources for continuous volcanic monitoring. International partnerships with Portugal and the United States provide periodic surveillance, but real-time observation remains challenging. The island's economy depends heavily on tourism and wine production, both industries centered within the caldera. Pico do Fogo continues building within the ancient collapse structure. Each eruption adds material. Each adds weight to an edifice sitting inside evidence of its own past failure. The caldera walls stand as a warning written in stone. Yet inside those walls, life continues. Residents of Chá das Caldeiras understand the risk. They accept it as the cost of home. Fire Peak will erupt again. The question is only when. Mount Rainier dominates the Washington skyline at 4,392 meters. On clear days, the mountain is visible from Seattle, 87 kilometers to the northwest. It is an icon of the Pacific Northwest. A landmark. A symbol. It is also one of the most dangerous volcanoes in the United States. Mount Rainier last erupted in 1894 with minor steam bursts. Its last major eruption occurred approximately 1,000 years ago. But the volcano's greatest threat does not require eruption. It requires only gravity and water. Mount Rainier holds approximately 35 cubic kilometers of glacial ice, more than all other Cascade volcanoes combined. Beneath that ice, the mountain is decaying. Extensive hydrothermal alteration has chemically weakened the summit and upper flanks. Superheated groundwater transforms solid rock into clay-rich material over centuries. The result is a structurally compromised edifice covered in massive glaciers sitting above river valleys filled with people. The United States Geological Survey rates Mount Rainier as a very high-threat volcano. Not primarily because of eruption potential, because of lahars. Lahars are volcanic debris flows, mixtures of water, rock, mud, and ice that travel at highway speeds down valleys, burying everything in their path. Mount Rainier has generated catastrophic lahars repeatedly. Approximately 5,600 years ago, the Osceola mudflow mobilized an estimated 3.8 cubic kilometers of material from the volcano's summit. The flow traveled over 120 kilometers, reaching Puget Sound and covering areas now occupied by suburbs south of Seattle. More recently, approximately 500 years ago, the electron mudflow reached what is now the Puyallup River Valley. Over 150,000 people currently live on deposits from these ancient lahars. USGS hazard maps show their homes lie directly in future lahar inundation zones. The threat is not hypothetical. Even without eruptions, glacial outburst floods occur periodically when meltwater accumulates beneath ice and suddenly releases. Climate change accelerates glacial melting. Ice that once buttressed weak rock is disappearing. The risk of collapse-triggered lahars may be increasing. The USGS maintains continuous monitoring through seismic networks, GPS stations tracking ground deformation, and automated lahar detection systems installed on the volcano's flanks. These acoustic flow monitors are designed to detect lahars as they occur and transmit warnings downstream. The system could provide approximately 40 minutes of warning for evacuation, if it functions perfectly during an actual event. 40 minutes to alert over 150,000 people. 40 minutes to evacuate valley communities before flows traveling at 80 kilometers per hour arrive. Mount Rainier has not produced a major lahar in 500 years, but geological records confirm the pattern repeats. The mountain will generate lahars again. Seattle's slumbering giant does not need to wake fully to kill. It needs only to shed what it carries. Kīlauea erupted nearly continuously from 1983 to 2018. For 35 years, lava flowed from vents on the volcano's flanks. Visitors came from around the world to witness molten rock entering the ocean. The eruption added approximately 500 acres of new land to Hawaii Island. It became predictable, routine. Then, in May 2018, everything changed. On May 3rd, fissures began opening in the lower East Rift Zone, 40 kilometers from the summit. Lava erupted through residential streets in Leilani Estates. Flows advanced through neighborhoods, consuming homes one by one. Over 700 structures were destroyed. Lava covered 35.5 square kilometers. But the crisis at Leilani Estates was only half the story. At the summit, something unprecedented was occurring. Magma was draining from the shallow reservoir beneath Halimaumiu crater. The summit was collapsing. Between May and August 2018, the summit subsided over 500 meters, equivalent to a 50-story building dropping into the earth. The collapse occurred through 62 distinct events. Each produced earthquakes ranging from magnitude 4.7 to 5.4. Sometimes multiple collapse events happened in a single day. Hundreds of earthquakes shook the summit area daily. USGS scientists at Hawaiian Volcano Observatory watched in real time as the landscape they had studied for decades reshaped itself within months. Monitoring equipment recorded every tremor, every centimeter of subsidence. Yet predicting the exact timing and magnitude of each collapse remained impossible. The 2018 sequence demonstrated that even the world's most closely monitored volcano can behave unpredictably. Kilauea's instability extends beyond its summit. The volcano's entire southern flank is moving. Gravitational spreading pushes it seaward at approximately 6 to 10 centimeters per year. This constant movement stores stress within the rock. On November 29, 1975, that stress released suddenly in a magnitude 7.7 earthquake. The earthquake triggered a local tsunami. 2 people camping at Halate Beach were killed when waves swept the coastline. The southern flank continues moving today. The stress continues accumulating. Hawaiian Volcano Observatory maintains continuous surveillance through dozens of seismometers, GPS stations, gas sensors, and tilt meters. Yet infrastructure and communities exist on active rift zones. Residents live knowing the ground beneath them is mobile. Tourism depends on the volcano. Hawaii Volcanoes National Park attracts millions of visitors annually. The economy and the threat are inseparable. Since 2020, Kīlauea has resumed erupting inside Halima-Umiu crater. A new lava lake is forming where collapse occurred just years earlier. The volcano is rebuilding itself. Kīlauea is not unstable in the way a structurally weakened edifice is unstable. It is unstable because it is fundamentally dynamic, constantly moving, constantly changing, constantly reshaping the island. The shapeshifter of Hawaii never stops. Mount Etna rises approximately 3,357 meters above eastern Sicily. The height is approximate because it changes constantly. Summit craters build and collapse with each eruption. The mountain grows, then shrinks, then grows again. Etna is Europe's highest and most active volcano. It erupts almost continuously. Between 2021 and 2023, the southeast crater produced some of the most intense activity in decades. Paroxysmal eruptions sent lava fountains over 1,000 meters into the air. Ash plumes closed Catania's airport dozens of times, stranding thousands of travelers. Volcanic tremor shook the mountain. Explosions echoed across Sicily. And through it all, approximately 1 million people continued living on Etna's slopes. Catania, Sicily's second-largest city with a population of 310,000, sits just 30 kilometers from the summit. Families cultivate vineyards and orchards on volcanic soil that has been worked for generations. They know any eruption could destroy decades of labor. They stay because Etna's soil produces exceptional crops. The wine, the citrus, the pistachios, all depend on nutrients from volcanic ash. The 2002 to 2003 eruption demonstrated Etna's destructive reach when lava flows destroyed the Piano Provenzana tourist complex and severed the road to mountain refuges. Communities on the southern and eastern flanks evacuated as flows advanced. Infrastructure was damaged. Economic losses mounted. But Etna's greatest threat may be invisible from the surface. GPS monitoring reveals the entire eastern flank is moving toward the Mediterranean Sea at approximately 2 to 3 centimeters per year. This is not earthquake-related motion. This is gravitational sliding, the mountain's immense weight pushing against underlying sediments. The eastern flank is slowly detaching. Currently, the movement is gradual, continuous, measurable. But geological evidence suggests Etna has experienced catastrophic flank collapses in the past. If the eastern flank were to fail suddenly, the resulting landslide could enter the Mediterranean and generate tsunamis affecting multiple countries. Italy's National Institute of Geophysics and Volcanology operates over 70 monitoring stations across Etna. Seismometers track earthquakes. GPS networks measure deformation. Thermal cameras observe summit craters. Gas sensors analyze emissions. It is one of the most comprehensively monitored volcanoes on Earth. Yet prediction remains imperfect. Etna's behavior is complex. Magma pathways shift. Eruption styles vary. Flank eruptions, which occur lower on the slopes, pose greater hazards than summit activity because they threaten populated areas directly. Despite constant threat, Etna is a UNESCO World Heritage Site. Tourism brings essential income. Agriculture thrives. The volcano and the people exist in calculated coexistence. Sicilians have lived with Etna for millennia. They understand the risk. The mountain provides. The mountain threatens. Both truths are accepted. Europe's restless giant will continue erupting, continue growing, continue moving toward the sea. And the people will remain, watching, adapting, enduring. These 8 mountains show that volcanic danger does not come from eruptions alone. Some fail slowly. Others collapse without warning. Events like the Anak Krakatau tsunami and the collapse of Kīlauea's summit prove that even closely monitored volcanoes can surprise us. Millions of people live on these unstable slopes today. Understanding how and why these mountains fail is essential. If this documentary helped you see that risk more clearly, subscribe for more real, evidence-based mountain documentaries.